All right, welcome. So we're going to go ahead in this video, we're going to take the Laplace transform of power functions. Okay, so that means we're going to take the Laplace transform of t to the n. Okay, I should put of s, of course. So that's, again, the integral from 0 to infinity, t to the n, e to the negative st, dt. Okay, so the way we're going to do this is actually a great example of what's called mathematical induction. So that's a good reason to sort of study this, especially if any of you think you're going to be doing a little more math in this class, okay, than this class. If you're going to be going on in math or something that uses a lot more math, you will want to know mathematical induction. It's a standard tool that we use, okay? So we're going to start by proving this for just n equals 1. We're going to start with doing a few cases. Or let's start with n equals 0. That's the easiest case. That's the easiest case. We're going to take the integral from 0 to infinity, e to the negative st dt. Okay, we've already done that. Okay, look just right back over here. That's 1 over s. Okay, let's take n equals 1. So the integral from 0 to infinity of t e to the negative st dt. Now here we're going to have to do this by integration by parts. Okay, so we're going to let, whenever we have, remember we have a polynomial times an exponential, so we're going to always let u be the polynomial. So we're going to have u equals t, dv is e to the negative st dt, du is dt, and v is negative e to the negative st divided by s. Okay, so we're going to get uv from 0 to infinity plus, because of this minus, okay, that minus and the minus that comes from integration by parts become plus. The integral from 0 to infinity, what is it? E to the negative st divided by s dt. Okay, so let me rewrite that just a little bit. Well, let's not. This part, that becomes 0 at its endpoints. Okay, at 0 you've got the t, and at infinity the e to the negative st becomes 0. Okay, so this becomes, or this is, 1 over s times, I'm going to write the Laplace transform of 1. Okay, so that becomes 1 over s squared. Okay, so n equals 0, we got 1 over s. N equals 1, we've got 1 over s squared. Okay, so our goal in doing these first couple is to try to find a formula. So let's do another one. Let's see if we can use n equal 2 to help us find the formula. For n equals 2, we're going to take the integral from 0 to infinity. That's now t squared e to the negative st dt. And we're going to do the same thing we did. Okay, so we're going to do our u is, of course, t squared. Our dv, e to the negative st dt. du is 2t dt. And v is e to the negative st divided by negative s again. Okay, so now, when we put these together, uv minus v du, so that's going to be negative t squared e to the negative st over s, 0 to infinity. Again, let me use a lighter color there so that you doesn't cover up what you're trying to see. Again, that's going to go to 0. Let me change that orange too. Sorry, it was bothering me there before. I just couldn't let it go. Okay? Minus, but the minus from integration by parts together with this minus s is going to become plus. This time I'm smart enough to realize, you know what? Let me pull out that s. The integral from 0 to infinity. Okay, and now I have 2 t e to the negative st dt. Okay, I'm even smart enough, I'm going to pull that 2 out in front here. Okay, so now this becomes, or this is 2 over s times the Laplace transform of t. So that becomes 2 over s cubed. Okay, now we're starting to see a pattern form. Okay, so now we're gonna assume our pattern. Okay, so we're gonna assume, make this a little smaller. Okay, so we're gonna assume that we have that the Laplace transform of t to the n is going to be actually n times the Laplace transform of t to the n minus 1. Okay, so that's going to imply that the Laplace transform of t to the n equals n factorial, okay, over s to the n plus 1. Okay, so let's see how that works. Okay, so just where this factorial is coming from. Okay, here 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1. And then when I do the n equals 3, I'm going to get a 3 here times the Laplace transform of t. But let me actually prove that. Okay, so now I have to prove the induction step. Okay, so we assume this is true. Okay, so we assume this is true. We're going to show what happens for the next one. Some people will assume it for n minus 1. I like assuming it for n and then showing it's true for n plus 1. Okay, so assume it's true, and then we're going to do it. So ln of tn plus 1 equals, of course, the integral from 0 to infinity t to the n plus 1 e to the negative st dt. Okay, our u is, of course, t to the n plus 1. Our dv is e to the negative st dt. Our du is n plus 1 t to the n dt. Okay. And our v is e to the negative st divided by negative s. Okay. So now the uv minus v du, t to the n plus 1, e to the negative st divided by negative s from 0 to infinity. That's still going to be 0 at its endpoints. That's going to be 0 at 0, and as it goes to infinity, the e to the negative st dominates. Okay, minus the integral from 0 to infinity. Again, just like the other cases, this minus, okay, by the way, I should have checked this. That should have had an s there. Sorry about that. As we're seeing now, right? That minus is going to combine with this minus to become plus. This n plus 1 and the s, I'm going to go ahead and pull out. Okay, and then I'm going to have t to the n e to the negative st dt. Okay, so our Laplace transform of t to the n plus 1 is n plus 1 over s times the Laplace transform of t to the n. Now, here we go back. This is our assumption for Laplace transform of t to the n. So n plus 1 over s times, let me write that in orange, n factorial over s to the n plus 1. Make things just a little bit smaller. To finish up. I don't even need to. I just move it up. Okay, so now the last thing that we do is then we conclude Laplace transform of t to the n plus 1 is n plus 1 factorial over s to the n plus 2. Okay, so just real quick, let's just overview what happened with induction. Okay, so with induction, what we did here, and what you should normally do, is find a few terms, find a few early terms. Basically, you find as many as you need to find the pattern, okay? I did 0, 1, and 2, and after that, I was able to guess what the pattern. Guess the pattern, and then you assume the pattern. Okay, so what we're really doing when I say we're assuming the pattern, we're assuming it holds true for some n, and it does. When we guessed it, we know that it holds true for n equals 2. Okay, so we assume the pattern for a given n. Okay, and then the third step is that you show that the pattern at n implies that it works for n plus 1. Okay, so what have we done here? Let's say that our n here is 2. Okay, we're going to show that we know how to find it for 3. But then once we found it for 3, guess what? We can find it for 4. We can find it for 5. We can find it for 6. We can keep on going forever. I've proven an infinite pattern with a finite amount of steps. Okay? All right, I'll see you all in the next video.